Okay, part two on the videos for section 5.5 is basically just working this example, which is example 5.3, and we'll pull up a schematic of this Warren-Leonard control system and put some real numbers in it and see if we can figure out what's going on with it. So here's our system with some numbers as specified in example 5.3. First off, it says that there is a 2000 kilowatt, 500 volt variable speed motor. Okay, so that is here, 2000 kilowatts, 500 volts, variable speed DC motor. It's being powered, or it's being supplied, I guess I should say, by this 2500 kilowatt generator that we're looking at here. And it says the total resistance of the motor and the generator armature circuit is 10 milliohms, okay? And I'm just going to put that right here, and that encompasses the total resistance in both the motor and generator armatures. And it says that the motor will turn at 300 RPMs when the voltage on the armature is 500 volts. Okay, so he's asking us some particular questions. What's the motor torque and speed when the E sub S value is 400 volts? Okay, and when E sub O is 380 volts. All right, so we're going to work through that, and then we're going to change this out, and we're going to reverse this in part B. All right. So let's work through this. So let's see what we can come up with and see if this helps make sense of how this control system works. So here's our first situation. What we're going to do is we're going to figure out what the armature current is, and it's going to be equal to, current is equal to source minus armature divided by the resistance. Put some numbers in here. Source in this first part is 400 volts. E sub O, the armature voltage, is 380 volts. Okay, so we'll do that subtraction. And then the resistance is 10 milliohms, or we could just say 0.01 ohms. All right, now that seems like a very, very small amount of current, but you watch when we start dealing with some very, very large currents, that small resistance is pretty significant. So if I go through and I crank this out, look what the armature current is for this situation. It's 2000 amps, okay? 2000 amps would be this value right here. Okay, now if we wanted to calculate what the power to the motor armature is, okay, it's going to be this voltage times that current. So let's clear something out here. Put it down here. Okay, so we've got the power to the motor armature is E sub O times I, or 380 volts times 2000 amps, and we find out that that is going to be 760 kilowatts of power to the motor armature. Okay, so let's hold that thought for a second. Okay, we've got the power to the motor, and he's asking us what the motor speed is going to be. So here's a problem. Again, it's like some of the other things that we've done. We're given one value. We know at 500 volts, we're at 300 RPMs. So we'll use this as a proportion, okay? And what we'll try to figure out is if we're at 300 RPMs and 500 volts, what would the speed be at 380 volts? And we're calculating what that X value would be. Okay, so we solve for X. We multiply that through, and we've come up with that the motor speed is 228 RPMs, okay? Again, assuming this linear relationship, which we can assume in this DC motor setup. So at this point, you know, you got all this stuff going on. You must be thinking, now what were we doing? Well, what we're doing is we're trying to find the motor torque and speed. All right, so we got the speed, right? We know the speed at 380 volts. Now, what is the torque? We have an equation for that. We can use this power of a motor formula solved for torque, which is going to give me 9.55 times the power divided by the speed. Okay, and so 9.55, the power is 760 kilowatts. I think I've erased that, but that was, oh, here we go. It was right here, right? Based on the current and the voltage. And then this is divided by 228. We're looking for torque. Of course, it's going to be in Newton meters. And we come up with 31.8 kilonewton meters. So that is the torque at the conditions that were given originally. And that's how we were able to come up with that. And since the current is going into the motor, into the positive terminal, you know, we'll say this is a, we'll call this a positive torque. All right, now let's change the conditions and see the operation of this speed control system. All right, now for part B, the situation's changed a little bit. The armature voltage is going to stay at 380 volts. Okay, now we just went through you know, an involved determination to know that at 380 volts, we're turning at 228 RPMs. All right, so we got that. Let me get rid of this, give us a little room to write on here. And then so now this is still at 380 volts, but look at E sub S, it's decreased to 350 volts, okay? So that doesn't apply anymore. And of course the resistance doesn't change. So this doesn't work anymore because that was based on a particular current that we're not using anymore. And so now we need to go through and determine, first off, the current. So the current for this current is equal to E sub S minus E sub O. I'm going to write that up here for a reason. And then I'm going to divide that by our resistance, 0.01. Okay. And then now this is 350 minus 380 divided by 0.01. And that now gives us a current of 3,000 amps. But what we need to do is we need to designate this as negative because this current now has changed directions and is actually going this way toward the generator. The current's negative, so it flows in reverse. Consequently, when the current changes direction, the motor torque reverses. It's slowing down. So the power returned by the motor to the generator and this resistance is going to now be power is equal to E sub O times the current, which for us is 380 volts times this new current of 3,000 amps. And we find that to be 1,140 kilowatts. Okay, so what we need to think of, and this is something that we maybe not have thought about this before, but when the current reverses direction, the torque reverses direction, the motor is slowing down. So we think of this in terms of it being a braking torque. So in the next part here where he's asking us what is the torque in this problem, okay, we just calculate it like we did before. That's no problem. 9.55 times this power of 1140 kilowatts divided by our speed, that is still 228. And now we have a torque of 47.8 kilonewton meters, okay? And because it's causing the motor to slow down, then we call it a braking torque, okay? Because it's causing this system to slow, a braking torque. All right, one little other section here. Let me pause this and we'll mention that, and then we'll be finished with this. He says the speed of the motor and its connected mechanical load will rapidly drop under the influence of what we call an electromechanical braking torque. And we'll explore this and put some words to this. One that you're going to start hearing a lot of is this idea of something called dynamic braking. Okay, and as we get ready to leave this section, one thing I did want to point out to you, I've included in Blackboard under content this slide too, that I went through and I took this same system and I just came up with these things that are going on, right? And what I'd like for you to do is as you try to understand this and try to wrap your brain around this, just walk through these, and it says motor armature M, connect it to a separately excited DC generator G. Just make sure that you really grasp all this. So, I wanted to put that slide in there. And then the last thing here, he says we could also do speed control through a rheostat. And what he's saying is, as you look at this, you place a rheostat in series with the armature. Okay, so that would be this. This would be the rheostat. And I can adjust it. I can move it to this position for minimal resistance, and I can move it to this position for maximum resistance. And when it's at maximum resistance, then the excitation current I sub X will be the least amount in this shunt field consideration or configuration. And when it's here, this I sub X, the resistance is minimum, this will be maximum. And at that point, that is causing our equation, our flux to be maximum, and then the voltage would increase. So the current in the rheostat produces a voltage drop, and so you could use this situation to control the speed. Now, if you think about those currents that we were looking at, one was 2,000 amps when it was positive going in one was 3,000 negative in the opposite direction. This becomes a very inefficient way to control the speed. You think about all of that current going through that resistance and the heat that's generated, all of that kinetic energy that's returned to the system is just lost as heat. So it's not a very efficient way, but in some smaller motor applications, then a rheostat control might actually make sense in terms of controlling the speed. All right, so we'll wrap this up for section 5.5.